Okay, so we have two questions to discuss. Okay, basically we want to do the calculation for Earth three-phase fault current and Earth fault current. So we have two different approaches, right? The calculation methods. So we will illustrate those methods. Okay, by using the tutorial questions here. Okay. Okay, so let's look at the first question. Okay, so we have some information about the installation. We start from the transformer, so back to draw the schematic, simple schematic, okay, for better understanding. All right, so sit down here. So we start from the transformer, right? So the information about transformer is given, right? This is a 1.5 MVA or 1,500 kVA, okay, kVA. 11 kV over 380 volts, okay? And of course, this is connect from the HV circuit. So we are given by the fault level or fault rating here at the 11 kV side, which is 3 SSC is equal to, at the HV side, 350 MVA. Okay. All right, and of course, at the LV side, we have a switchboard, main LV switchboard. Okay, so let's put the LV switchboard here. Incoming circuit and outgoing circuit. Again, you have circuit breakers for those both incoming and outgoing circuit. And the outgoing circuit actually goes to a lift machine room for a lift motor. Okay, so let's say this is a low, okay, motor. Okay, and this outgoing circuit is made by using the bus start. Okay, this is the bus start. Okay, and the length L is equal to 240 meter, right? And bus start impedance is given, right? The resistance is equal to 0.031 milliohm per meter, and the reactance is given here again 0.115 milliohm per meter. Okay, and the switchboard impedance here is not given. Okay, so we can assume you can put small number here, or you just let it be 0. Okay, for a simple calculation, then you can consider it 0. Okay, and the transformer impedance here, the resistance value, okay, in percentage is equal to 0.5%, and the total impedance Z in percentage is equal to 6.5%. Okay, so that is the information, right, given by this, in the question at the beginning, right? So we want to find, okay, we have 3 questions, right? We want to find out the RMS value and the peak value. Okay, I think you can forget about peak value. So because we are not really need to know the peak value, okay, at this moment. Okay, just find the RMS value. The RMS value of 3-phase fault current. So this, let's say we have fault at the remote end. Okay, so this is a 3-phase fault. 3-phase fault current. So we want to find the 3-phase fault current. Okay, and part 2, okay, is based on the 3-phase fault current. We need to calculate the phase-to-phase fault current. Okay, again, this is not very important because what we want, okay, basically are 2 currents. Okay, one is the 3-phase fault current, one is the earth fault current. Okay, all right. So we'll do the question 1 first, and then we'll look at some other things later. Okay. Okay. So because we know everything about the circuit, and we can use the approach or the formula given in the lecture, right? To find out the fault current. So basically, the fault current, whatever. Okay, this is actually it's a three-phase fault current, right? Is equal to the phase voltage divided by the total impedance, right? And the total impedance includes the one for HV circuit, okay, which is determined by the short circuit capacity, okay, and the transformer impedance. Of course, switchable impedance here, we can let this one equal to 0. Okay, 0, because we are not given any information here. Okay, or you just put some small number here. Okay, okay, and then the bus that. Okay, so that is the way to find out the impedance, and then if the total impedance is given, then you can use the very simple formula that we call the Ohm's law to determine the three-phase fault current. Okay, and all the detailed information actually is given in the solution sheet. So let's look at the solution sheet. Okay. All right, so the solution gives us the step-by-step result. Okay, so the first one you can see is the result for the HV circuit impedance. Okay, we here called the network impedance. Okay, so this is impedance of HV circuit, but we are and we call it this HV circuit impedance referred to the LV side, because we're looking at the fault current at the LV side. We have to change the HV circuit impedance to the LV side. So we have a formula which is actually given in the notes. Okay, so what you need to do, just substitute those values. Okay, in this simple formula. Okay, so here VL is the line voltage in the LV at the LV side, okay, which is 380 volts. Okay, and the denominator here is the short circuit capacity, okay, or fault level, whatever we can call it. Okay, fault level, fault rating, short circuit capacity. Okay, the unit is MVA. Okay, or VA. Okay, so here is 350 times 10 to the power of 6. Okay, so the result is equal to 0.413 milliohm. It's relatively small. Okay, and here again, you know, when you do the calculation of impedance, you have to know whether this is the resistance value or the reactance value. Okay, because the total impedance usually is equal to the resistance plus Jx. Okay, R is a real value, and the other one, J, means the reactance, or it means it is a complex value. Okay, and so as we say in the lecture, the resistance value for the HV circuit, it could be 0. Okay, you can, because nothing is given here, so you can make assumption it is equal to 0. So that means the reactance X just equal to 0.413 milliohm. Okay. All right. So this is the HV circuit impedance. The next one is the transformer impedance. We have a similar formula. Okay. But in this case, we need to consider both resistance and the reactance together, because the information about resistance is given already, okay, here in the question. Okay, so we again, this formula is similar to the previous one. Okay, the impedance in percentage times the one we call the base value. Okay, again, it is the line voltage square over the rating of the transformer. Okay, so because everything here is given, right? The percentage of impedance is 6.5, right? And the line voltage is 380 volts at the LV side, and the transformer rating is 1,500 kVA, so it's 1,500 times 10 to the power of 3. Okay, so after the calculation, you can find it is equal to 6.257 milliohm. So actually, this one is the total impedance. You can say this is the absolute value of the Z. Okay, absolute value of Z. Okay, so then we can find out the resistance. Okay, because the percentage of resistance is given, and in a similar way, you can see it is equal to 0.4813 milliohm. Okay, so because you know the total impedance value, the absolute value of the impedance, and the resistance value, you can find the reactance value. Okay, so here is the way to determine the reactance value. Okay, so because the resistance value is small, so the reactance value is very close to the total impedance value. Okay, so not much difference. Okay, finally we can express the impedance of the transformer in this way. It is equal to 0.4813 plus J 6.2385. Of course, it may not be necessary to keep those 4 digits in the calculation, and most cases you can keep 2 digits. Okay, that be good enough. Okay, all right. So for example, in this case, you just say, okay, it is a 4 impedance of transformer is equal to 0.48, and the reactance is equal to 6.24. Okay, 2 digits would be fine. Okay, not necessarily have a 4 digits. Okay. All right, and the final one is the bus-step impedance. This bus impedance given here actually is called the phase impedance. So this is different from the impedance for the cable. And for the cable, we will show you later. Okay, you have to use the COP tables. Okay, and the COP table actually give us the result we call the line impedance. So you have to do the conversion from the line impedance to phase impedance. But for the bus-step, the impedance normally provided by manufacturer, okay, is actually the phase impedance. So nothing we need to do here for conversion. Okay, so we substitute those impedance value in the general formula here. Okay, so you can find out the total impedance. Of course, this one is 0. Okay, you can put a 0 here. Okay, and then the final result. Okay, you can see this is the complex number, right? In total impedance. So you have to find the absolute value. Okay, so first of all, you need to combine all the resistance real value together and imaginary number together, and then take the find out the absolute value. So here, of course, we do not we do not have such detail. Okay, but suppose you know how to do that, right? This is a very fundamental math knowledge. Okay, so after the calculation, the 3-phase fault current is equal to 6.258 kiloampere. Okay, again, you can say 6.3 or 6.26 kiloampere. Okay, that will be fine. Okay. Okay, so this is the 3-phase fault current. Okay, at the remote end. Okay, remote end of the circuit. And I think the calculation is pretty much straightforward. Okay, very straightforward. Okay, so what you need to do is just find out the impedance. Okay, for each item, and then add them together. Okay. And here we are talking about the 4 current at the remote end. Okay. But in the lecture, I said, okay, we need to find out the maximum 4 current in the circuit. The maximum 4 current certainly is a 3-phase 4 current. But remember, okay, when we're talking about the maximum 4 current, which means the impedance should be less, should be least, right? And for this circuit, the least impedance is observed if you have 4. At the beginning of the circuit. So the 4 at the origin of the circuit, we generate the largest 4 current. Okay, so if you want to find this current, okay, again you can use that formula, but the impedance so the impedance, of course, okay, you can add some switchable impedance, but this one is 0. Okay, you can say it's 0. So if you want to find the maximum 4 current, so you certainly we need to consider the 4 at the origin of the circuit. That means we do not need to include the bus stop impedance in the formula, in the calculation. So you can see if we want to find out the maximum 4 current, actually the circuit impedance, okay, is not included. We do not need to know the impedance of that particular circuit. We just want to know the everything up to that the circuit, okay, origin of the circuit or the beginning of the circuit. Okay. All right. So you can find out the maximum 4 current by yourself. Okay, because this is just a simple calculation job. Okay. It's nothing special. Okay, nothing special. Okay. All right. Any questions for this part? Okay. If no, then we move to part 2. We want to find the phase-to-phase for current, and I didn't say about the this for phase-to-phase current in the lecture because I do think this is not necessary. Okay, in most cases it's not required. But anyway, okay, here just a simple way, okay, to find out the phase-to-phase for current. Okay. Using the 3-phase 4 current results. Okay, so generally speaking, phase-to-phase 4 current, phase-to-phase 4 current is equal to 3-phase current multiply root square 3 over 2. So this is a constant value. Okay, this is a fixed constant. Okay. So if you know the 3-phase 4 current, you can find out the phase-to-phase current by using this factor, okay? This root square 3 over 2. And this one actually is approximately is 866, okay? So you know phase-to-phase 4 current certainly is less than the 3-phase 4 current. So that's the reason why we don't need to worry this one too much, because we are looking at the maximum 4 current, the largest value, okay? But the phase-to-phase 4 current is not the largest value. So that's why we do not need to worry too much about this one, okay? All right, okay, so this is the 3-phase 4 current. And let's go to the question for part 3, okay? So for part 3, actually, it's S4 current. Okay, so this case is different from the the circuit here. It's another circuit. Okay, so this one says we have a certain mid-long 3-phase 20 amp circuit protected by BS88 fuse. This is supplied from the transformer by the LV switchboard. and the circuit is composed of 4 mm² single core PVC cables, okay, running in the high-grade steel conduit, 16 mm diameter. So the cable, single core cable in the conduit, and this conduit actually is used as a protective conductor, okay. The earth's fault load impedance external to the electrical installation is approximately equal to 0.5 ohm, and you can ignore other parts, small stuff, okay? So that means you have a transformer here, and you have one outgoing circuit, okay? And this circuit, you have earth fault here, okay? And this circuit is made by the single core cable in conduit, okay? So we want to find the earth fault current, And remember, the formula for earth fault current, again, is 220 volt over ZS. ZS is called the earth fault loop impedance. Okay, so in this case, this is the earth fault loop impedance. Then through the earth. Okay, this is the earth fault loop impedance. Okay, earth fault loop impedance. Okay, and the earth fault loop impedance include the earth fault loop impedance external to this cable. We call it the cable is the electrical installation, okay, which is given in the question 0.5 ohm, okay, plus Z1, Z2 for the outgoing circuit. We have cable 1. In this case, we only have one cable, one circuit, okay, this is one circuit, okay. So that is the earth fault load impedance. This is 0.5 ohm, and this one actually include the impedance of the line conductor and the CPC, okay. So in this case, as I said in the lecture, we have a for the cable impedance, we have 2 different tables, okay. We can use 2 different tables to figure out the impedance for the cable. And if it's a 3-phase fault, and then we use the COP table, EMSD COP table. And for the earth fault, or the phase to neutral fault, which considers an unsymmetrical fault, unbalanced fault, okay, then we have to use the schedule, okay, okay. So in this case, we use the conduit as a CPC, so we have to use the schedule, okay, for that conduit, okay. So let's go to the solution first, okay, for that part, okay. So as you can see here, we have the formula listed here. Okay, Z equal to earth fault load impedance external to the installation plus the circuit impedance. Okay, and the circuit impedance can be obtained by using the column data in column C of the schedule, 2.11 and 2.12. Okay, let me see. Okay. 2.11, okay. Two point 11 is for the fault current less than 100 ampere, okay, and the 12 okay, for the current greater than 100. But at the beginning, okay, we don't know whether this is less or greater than 100. So you may try to use 2.11 first, okay, see whether the result is greater than 0 or less than 10. If not, then try to use schedule 2.12, okay? So the result here, okay, let's see, okay, actually give you in the solutions give you two results, okay. First of all, we use 2.11 and we find the impedance. So let's see the cable size, okay. The cable size is 4 ms squared, the conduit diameter 16, so we need to look at the combination of both, right? Okay, so here this is H grade, okay, heavy grade. So this is a heavy grade, right? Heavy grade, okay, and 16 meter, okay, cable size, and 4 millimeter cable size, 16 diameter for the conduit. So this is a combination, right? So here, this is the result, okay, 12.6. Okay, 12.653. So if you look at the solution sheet, that is a figure, okay, used, right, in the calculation. Okay, and of course, this is a milliohm per meter. Then you have to multiply this one by 30, okay, meter. So the total impedance is equal to 0.88 ohm. Okay, and then you can find out the fault current by using this the Ohm's law, and then you can see it is equal to 250 amp. And this one certainly is greater than 100 amp. So the schedule 2.11 is not adequate. We have to use the next one, okay, for the fault current greater than 100. So again, we use the HG, okay, high grade steel conduit, and the 4 mm, okay, and the 16 mm diameter. So the result, okay, here is column C is 19.121. Okay, 19.121. Okay, so use this result. We repeat the calculation, but use this figure for the impedance. So the total impedance in this case is higher than the previous one. Okay, it is equal to 1.07 ohm, and the result now, because the impedance increased, so the actual earth fault current reduced a little bit. It is equal to 205 ampere, but still is larger than 100 ampere. Okay, so we say schedule 2.12 is the one actually we use, okay, to determine the earth fault load impedance. Okay, all right. So this is the way to determine to find out, okay, the earth fault current. So here you see you have to use the schedule, okay, to figure out the impedance value. Okay, so you see there's some similarity, very similar, okay, procedure, okay, in both approaches, okay, but the difference is the determination of the impedance, okay. For the same cable, okay, you need to use different cables or schedules to find out, okay, the impedance value, okay. All right, and for other parts, okay, because we haven't talked about the fuse curve, so I'm not going to touch that part, okay, but certainly you can answer those questions when we've finished the discussion about the overcurrent protection. Okay, so I just skipped this part today, but you can go back to this part, okay, when we finish the discussion about the overcurrent protection, okay. All right, okay, so that is the question one. Okay, so any comments or questions raised for this part, okay? All right, okay, if no major question, then we'll move to the question 2 in the tutorial sheet. Okay, so question 2 actually is very similar to the first one. So if you don't have a problems with the first one, and I don't think that you have any trouble with second one, okay? So again, this case, okay, let me draw the schematic diagram first, okay? So again, we have a transformer, okay, three-phase transformer, similar transformer, okay? So this is a 1,500 MV kVA, okay? 11 volts over 300 volts, okay? And the short circuit capacity is similar, okay? Actually, and the impedance transformer, okay, a little bit slightly different, okay? RT is 1.5%, 1.5%. ZT is equal to 5.5%. Right, okay. And we have a LV switchboard here, okay. Something like this. And here we know the cables, okay. This is called a main circuit. Main circuit. The circuit connect the transformer and the LV switch is called a main circuit. And this main circuit is made by a single core cables. So this is a three-phase circuit. So at least we have one cable for L1, one for L2, L3, and one for neutral. So at least we need to have 4 conduct cables. Okay, but in this case, we know for each phase we have 3 single core cables. Okay, so let's say this is a L1, L2, L3, neutral, right? So here we have 3 cables. Okay, connect to for the connection between switchboard and the transformer. Okay, and this cable impedance actually is given. Okay, is resistance is equal to 0.04. Let's see. All right, so here is the information about this circuit. Okay, it is made by 3 single core cable for each phase. So overall we have 12 cables, and the resistance for each cable, okay, each cable is 0.04 milliohm, and the reactance is 0.08 milliohm, and the length is 10 meter. Okay, and we want to find out the impedance, okay, and also the three-phase fault current and the main LV switchboard, okay, somewhere here, okay, somewhere here, okay, the fault current, the maximum fault current or the three-phase fault current, same, okay. So in this case, again, we need to use their formula, okay. This is three-phase fault current, and the total in this case is equal to HV transformer, and the switchboard, of course, you can assume this. Well, no, in this case, okay, we have another thing, the cables, okay, the cables, and the switchboard. So switchboard here, you just let it be 0, okay, because nothing is given here. Okay? But this one we have to include, okay, because this is a 10-meter single core cables, okay. So the impedance for those cables should be included, okay, should be included, okay. All right. So one thing we need to know, okay, that because the impedance for the cable is given for each cable. We have 3 cables connect in parallel. So the total impedance of cable, if you have let's say 3 cables connect in parallel, okay, and each cable impedance is called Z, okay, and then total impedance, okay, you can go Z1, then total impedance is equal to Z1 divided by 3, okay. So if they are connect in series, you have a series connection, that means it's multiplied by 3. But if you connect in parallel, it's divided by 3. Okay, 3 is the number of the components for this parallel connection. Okay. All right. Okay. So the impedance here is 0.04 plus j 0.08 divided by 3 multiplied by 10. 10 is the length of the cable. Okay, cable. Okay, so now let's look at the solution sheet. Okay. Okay, so most of the steps, okay, are very similar to those in question 1. Okay, and so I don't think we need to go through all the details because they are basically the same. Okay, to find out the impedance of HV circuit and to find out the impedance of transformer. Okay, so look at this one. Okay, so here this is the total impedance, okay, for the cable, divide by 3, okay, after you divide it by 3, okay, divide by 3, okay, and then you add all together, okay, resistance together and the reactance together, okay, so you will come up with the result, okay, 35.64 kiloampere, okay, so that is a large fault current, okay, 35.6 kiloampere, okay, and actually the largest fault current we expect in the electrical installation, the largest fault current is 40 kiloampere. So you need to keep in your mind, okay, in the electrical installation, okay, in the LV electrical installation, the fault current will not exceed the value 40 kiloampere. Okay, so this is the largest, no matter what calculation result, okay, you can have, okay, certainly is less than 40 kiloampere, will not be more than 40 kiloampere. Okay, so this is the sometimes we call this the fault level, okay, at the LV side, okay, fault level. when we say the fault level or fault rating, whatever you call, okay, fault level or rating, okay, at the LV side is a 40 kilomA, okay, which means this is the largest fault current, okay, largest fault current, okay. Okay, yeah, that's the stuff, okay, given in the tutorial sheets, okay. Now I want to give you some exercises, okay, which is not given here. Basically is the fault current in the case if you have you have the cables, okay. So let's say in this case you have outgoing circuit here. This one is made by 4-core PVC steel wire armor. Okay, let's put here, okay. 4-core 400 mm square PVC steel wire armor PVC cable. One number, okay. And we want to find the fault current at the point. So let's say the distance here, the length, okay, let's say is whatever, okay, put some figure here, okay, let's say 50 meter. 50 meter. And I want you to find out the fault current, three-phase fault current at that point. Okay. All right. Okay. So in this case, it's three-phase current with the cable, right? Impedance. So we can use the formula as we said before. Earth fault current, right? The three-phase current, I use this one, and but the total impedance in this case, okay, I put here total impedance equal to ZSCHV plus ZT transformer and the cable. Okay, this cable is the main circuit. Okay, and the switchboard impedance again 0 here, and their second cable. So we call this is a 4-core cable. Okay, 4-core cable here. 4-core cable here. So everything here is the same as the one we showed in the tutorial sheets. Okay, so we need to include the additional one here. Okay, so how can we find this impedance? And this impedance, okay, we have to use the COP table to find out the resistance value and the reactance value. And this 4-core cable is equal to R is the table value for resistance, and multiply by 1.15. Okay, if you look at the notes, okay, there's a formula for the cable impedance. Okay, I just copied the formula. Okay, and the reactance divided by rho square 3, and rho square 3 means the conversion from the phase line impedance to phase impedance current, because the COP table just show the line impedance, and multiply by the length. Okay, so this is the way to determine the cable impedance for three-phase fault current. And Rx can be obtained from the table, okay, COP table. So let's say the COP table for PVC armor cable. So this is the table, okay, multi-core armor PVC cable, okay, and we're looking at the impedance, okay. So this is a table A64. So the second part of A64 shows the impedance value. So the size is 400 mm square. You know, the bottom one is 400 mm square, right? So the result here is the resistance value is 0.1, reactance value is 1.125. Okay. Okay. All right. So this is actually the result. So I don't have a final answer. Okay, but you can calculate it by yourself. You can calculate it by yourself. Okay. So after you got the result, then substitute. Okay. In the formula here, and then back to this one. Then you can find the three-phase fault current at that point. All right. Okay. Okay. So I think that's all I want to talk about today. Okay. Just show you how to do the calculation to find out the three-phase fault current and the earth fault current using different tables, okay, schedules or the COP tables. Okay, just make sure don't mix those tables up. Okay, sometimes students use the wrong table to get the impedance. Okay, so make sure okay what table you need to use for that particular type of the faults. Okay. All right. Any questions you want to ask? Okay. If no, then we dismiss the tutorial session today. Okay.